Hi, everybody, and welcome to today's NCDS DataBytes lunchtime webinar. Today's speaker is Casey Dietrich. He is an assistant professor in the Department of Civil Construction and Environmental Engineering at North Carolina State University, and his research focuses on the computational modeling of coastal hazards, and that includes hurricane waves, storm surge, flooding, and pollutant transport. Casey received 3 degrees from the University of Oklahoma before moving to Notre Dame for his PhD in civil engineering. He has developed and validated high-resolution computational models of hurricane waves and storm surge along the Gulf Coast, and these models have been used for levee design by the Army Corps of Engineers and for floodplain risk assessment by the Federal Emergency Management Agency. Casey has also applied these models in an operational framework to forecast storms, including Hurricane Isaac in 2012, as well as oil transport following the BP oil spill in 2010. Today's talk is titled Mapping and Visualization of Coastal Flood Forecasts for Decision Support. And the talk will last about 30 to 40 minutes, and we'll have time for Q&A at the end. And as usual, we ask you to type your questions into the chat box. We'll hold them till the end of the talk and then read them back to Casey and let him answer. So, without further ado, I present Casey giving what I think will be a very timely talk.
Thank you. Thank you for that introduction. I just checked. We scheduled this talk on January 10th, and only the luckiest forecast models would have known at that time that this would occur right between 2 really big hurricanes. And so I think this is a timely talk, and really that work that we did as part of that data fellowship is really beneficial. So I'm Casey Dietrich. I'm part of a much larger team, and so there's several other names here on the title slide. My 2 graduate students, Nelson Toll and Rosemary Syriac, have contributed to this work, especially Nelson. This is forming the majority of his master's work at NC State. And then we also collaborate a lot with Jason Fleming, Brian Blanton, Corolla Kaiser, Rick Ludick, and many others who contribute to a community of coastal ocean modelers and storm forecasters. So the first part of this talk is going to be a little more general, and it's really other people's work that I'm going to show to kind of set the stage. And then after about a third to a half of the talk, we'll transition into the work that was done as part of this data fellowship. So we are all part of the ADCIRC model group, and ADCIRC is a model, coastal ocean model for coastal circulation, and in the last 12 years or so it has really gained a lot of strength for coastal flooding, especially during hurricanes. So this is an example of what our model can do. This is Hurricane Arthur, which moved through coastal North Carolina in 2014. It was a pretty small storm. It was just big enough to ruin the 4th of July for everyone at the beach, and then it was pretty quickly forgotten. But here you can see the vectors are the wind velocities. You can see the counterclockwise rotation as the storm moves through the system. And then the colored contours are the water levels. Early in the storm, water gets pushed across Pamlico Sound and up into a couple of these river estuaries, kind of on the backside of some of the Barrier Islands here. And then as the storm moves over the sound, that water tracks along with it and gets pushed against the sound side of Hatteras Island. And we get storm surge or water levels, maximum water levels up to 2.5 or 3 meters. So not the worst storm that has impacted coastal North Carolina, but this is the kind of simulations that we are trying to do. How high does the water get? What areas will be flooded, and for how long? We do this by using unstructured meshes. This is the unstructured mesh for North Carolina, and you can see we use thousands or even millions of these triangular elements. Out in deep water, you can see each of the elements, each of the triangles, But then in the near shore, and especially where we really care about the accuracy of our solution, we shrink down those elements and we put a lot of them in those regions. So there's a lot of elements in some of the inlets into the sound, a lot of elements along the Barrier Islands, and then inside the sounds, a lot of elements of some of these river estuaries and some of these navigation channels. So the more elements that we use in an area, the more accurate our predictions are. And so this is the model for North Carolina. This isn't the whole model, this is just a zoom for this specific region, but the model extends out into the Gulf and into the Caribbean and out into the Atlantic Ocean. And we have other models that we would use for other parts of the coast, like Florida or Louisiana or Texas, and I'll show some simulations from those later in the talk. But the idea here is it's unstructured. We have complete control over where we put these elements and thus where we're doing our computations. On that mesh, we use two models. We use ADCIRC, which is a model for long waves like tides or storm surge. So these are, you can think of these as waves that have periods of 12 hours or 24 hours or even longer. And we can resolve those waves and show how the tides change along our coast, how the storm surge will behave. And to do that, we need wind forcing, tidal forcing at our boundaries. Sometimes we bring in river flow if we're including rivers in our coastal model. We need that unstructured mesh. We can compute those long waves. And then that model communicates during the simulation with a second model called SWAN, which solves for the short waves. Those are the kinds of waves that you would see if you're sitting at the beach. So the wind sea and the swell, they have periods of a few seconds up to 30 seconds maybe. So the kind of waves that would devastate a building during a storm. So those two models pass information between each other. And then at the end of the simulation, we've got output of water levels, water velocities, wind speed, significant wave heights at every vertex of all those triangles in our mesh. And we can do this in real time. And so we try to run these models, SWAN and ADCIRC, in real time via an automated system called the ADCIRC Surge Guidance System. This is run at RENC, and it is operated by Jason Fleming of Seahorse Coastal Consulting. And if everything is running smoothly, then nobody has to do anything. The models are initialized, they're run and processed by scripts. Everything happens automatically. It senses when a new meteorological forecast is ready, it brings it in, it spins up the simulation, and post-processes the results. During a storm, we're taking advisories from the National Hurricane Center. So roughly every 6 hours, every time that they issue a new forecast advisory, we sense when that forecast advisory is issued. We bring it in and we use it to generate a wind field and then force our models for waves and storm surge. And so doing this right now for Hurricane Irma, we did this a couple weeks ago for Harvey. We've done this for the last several years for all of the major storms. The guidance can be shared in multiple formats. First, I want to talk about this web service. So if you go to adcirc.org and follow some of the links, you'll get to pages like this. So this is an example of the web service where we post our forecast guidance. And on the right side of the page, there's a couple of different options. I've selected the maximum water height for this forecast, and this was from last year. This is Hurricane Matthew. This is Advisory 27, which was issued on Tuesday. If you remember, Matthew moved closest to North Carolina on Friday night, Saturday. So this forecast is about 4 days before Matthew's closest approach to our state. And this was kind of the worst case. At this point on Tuesday, they thought the storm was going to move closer to North Carolina. They thought it was going to be a more powerful storm when it got to North Carolina. And so you can see the contours go up to the red here along the coast from Wilmington up to Morehead City. The red in this image is up to 10 or 11 or 12 feet. So this would have been a devastating flooding event if the storm had followed this forecast. Luckily, the storm changed. It moved a little farther offshore. It wasn't quite as strong of winds, and it became more of a rainfall event. So there was a lot of rainfall during the storm and then in the week after, and a lot of flooding of a lot of these coastal communities. This year, you can follow links through and see forecasts for the Texas coast. This is a forecast for Hurricane Harvey, which was issued on Friday the 25th of August, so less than a day before the initial landfall of this storm. You can see the storm approaching from the Gulf and moving over very close to Corpus Christi and pushing a lot of storm surge in our predictions between Rockport and Port Lavaca. And so this is a Google Maps application. You can click around and zoom in and see neighborhood level flooding. One thing that we do is try to do some perturbations of the storm. So what would happen if the storm followed a slightly different track or was slightly stronger or moved slightly faster than what is forecast by the National Hurricane Center. And so, for example, for Hurricane Harvey, this is the official forecast for Advisory 21, but we also did a perturbation where we moved the track right, so a little farther east up the coast, and you can see now that the landfall's moved north of Rockport, and a lot more water is being pushed up past Port O'Connor and Port Lavaca into this estuary. So this is starts to come at some of the uncertainty in these forecasts and what would be the resulting storm surge and flooding if the storm track changed a little bit. And hot off the presses, this is an advisory for Irma. This is just this morning, Advisory 29. The track has been changing in several of these advisories. This one, this morning, the track moves over the Florida Keys and very close to Miami, and you're seeing a dark red, purple color that is more than 10 feet of water in this range from South Beach down to the Florida Keys. So if this forecast was exactly correct in its track and its intensity and its forward speed, then South Florida would see some pretty devastating flooding of all these populated regions. But this forecast is already out of date. I was looking just now, and the National Hurricane Center has moved the track even farther east in its latest advisory, and a lot of the ensemble models are even farther east from the National Hurricane Center. So that it might follow a track that's closer to Matthew, where it's a little farther offshore of Florida and moves up the east coast and maybe makes landfall farther north. And so time will tell, but that could be problematic for North Carolina. So that's the web-based guidance. Some partners prefer guidance in other formats, and so as part of an earlier project that was supported by Sea Grant, my grad students and I worked on automated scripts that will convert our model output into GIS shapefiles and into Google Earth KML files, and then we can mail these directly to users who prefer these formats. And so one big user has been the North Carolina Emergency Management. They want to see our results in these formats so that they can combine them with some of their other data sets for building infrastructure, for roadways, and for other data points that they use in their decision making. So this is included, this script is included already in the ASGS. It's run automatically, and we're producing these shapefiles and Google Earth KML files. So here's an example. This is Hurricane Arthur again, but now it's an animation that we made from a GIS shapefile. So these are taken screenshots from ArcGIS that have been moved together, and you can see the storm moving through, pushing water around in the Sound, and then pushing it against the Sound side of Hatteras Island. It's not the best format for these kinds of animations, but it's really nice if you have other geospatial data sets that you want to combine with. And so just real quickly, that script is called Kalpana, and it utilizes several Python libraries to do its visualization, and it is very compatible with the ADCIRC output, both the maximum values and the full-time series. And we've been doing that for the last couple of hurricane seasons. But we got feedback from North Carolina Emergency Management that product could be improved quite a bit. And so this is where I'm kind of transitioning into the work that was done as part of the data fellowship. We want to enhance the flooding guidance that we provide to North Carolina Emergency Management. Our unstructured mesh, we're computing water levels and water velocities and wind speeds and wave heights at a total of about 600,000 points, 600,000 vertices in those triangular elements. And the smallest elements have spacings of 50 to 100 meters. There might be some locations down near Wilmington where it's smaller than that, but mostly along the coast, 50 to 100 meters is our minimum. So all on the barrier islands, 100-meter spacing. Every 100 meters, we know what the water level is we're computing in, but nothing finer than that. NC Emergency Management has some very high-resolution data sets for topography along the coastline, and they gave us a data set with spacings, regular spacings of 50 feet, but they have a much finer. They're taking the topography from LiDAR, and its accuracy is down under a foot now. So that's the kind of resolution that they want to see. If we can provide our guidance on spacings of 50 foot or smaller, then that becomes more meaningful when they compare it with some of their other high-resolution data sets. And there's a big difference here. We're computing on 600,000 points, but this 50-foot structured raster DEM that they gave us has 400 million cells just in the North Carolina counties, so just the 32 counties that intersect with our model. So several orders of magnitude difference in resolution here. So the goal, two things that we want to do. We want to downscale, so we want to take our resolution of 50 to 100 meters and shrink it down to 50 feet or smaller. And we want to extrapolate. We want to take our flooding guidance, especially the wet-dry fronts, so the extents of our flooding, and take them even farther into small-scale regions that are not represented at our 100-meter resolution. And so there's a little cartoon here that kind of visualizes this. So this is a cross-section of a beach. The mean sea level is this dark blue line. So normally this coastal house and these houses and maybe this roadway are above sea level. They're normally not flooded. But during a storm event, the water level is increased, and this light blue represents the resolution in our ADCIRC model. So this might be the side view of one of the triangles in our mesh, and it has a length on this side of 100 meters, something like that. The high-resolution topography that NC Emergency Management uses might have spacings that are much smaller, 50 feet, and so they have a much better representation of the shore and up to the roadway and up to some of the other infrastructure. So when we downscale, we want to increase the resolution inside of our model, but we also want to extrapolate and maybe take this water surface a little farther inland, maybe show that this roadway should be flooded, and maybe this building should be impacted. We just aren't able to model that in the resolution of our unstructured mesh. They probably are flooded in real life. We're just not able to represent that if we're trying to model the entire coast. So goal, enable data-driven decision-making for coastal communities, especially by connecting with NC Emergency Management, and any guidance that we give them is going to trickle down to the local emergency managers and the local coastal communities. We want to downscale and extrapolate our ADCIRC results to intersect with this higher resolution DEM. We want the process to be fully automated so that it can be incorporated into the real-time forecasting system. And we want it to run really fast. So we don't want to spend more than 10 or 20 minutes post-processing after we've already spent 60 or 90 minutes running AdCIRC and providing the initial forecast of the storm surge. And another objective, we want to use open source software. So we wanted this to be able to transfer from NC State to RENC, from NC State to Louisiana or Texas or Florida or anywhere else that it might be useful. So to do this, we use the GRASS GIS system. So this is an open source geospatial software that's developed partly here at NC State by Professor Matasheva and her group in the NCSU Center for Geospatial and Analytics. And it's a little different from something like ArcGIS in that it is, well, it's open source for one. We can put it on our cluster and use it free of charge. And it is really tuned for processing of raster data. So this 50-foot regular spacing, 50-foot everywhere DEM that we're using, we can operate on it really fastly using this GRASS system. So general steps: take the ADCIRC data from its resolution and interpolate it down to the resolution of the DEM, then extrapolate into the beach or into the small-scale channels and floodplains by expanding that raster outward only where the ADCIRC water levels are greater than the ground surface. So we need to do some sort of check to see does it make sense physically to extend our water levels into some of these regions. And we want to be sure to remove any cells that are not hydraulically connected. So we don't want to jump over a coastal dune. We don't want to go around or over a raised highway because water would not normally be able to flow over those, at least if the water's not high enough. So we want this to be still as physical of a surface as we get, even if we are post-processing in a geospatial sense. And then at the end, take this new grown raster and convert it back to a shape file that we can email to NCDM or any of our other interested end users. So another toy example here, this is a 2D example, just showing how the process works. So first, think of this like the DEM. This is maybe the 50-foot DEM that the NC Emergency Management provided. And this is a very idealized toy problem, but pretend that this is an estuary. So in the middle of the estuary, this white region, there's no data because this is below sea level, this is open water. And then on the sides of the estuary, the ground surface starts to slope upward. And so this light gray is a 1-foot elevation. The next lighter gray is 2 feet, all the way up to 5 feet at the top of the image, and all the way to 3 feet at the bottom of the image. On top of this, pretend that we ran ADCIRC and we got a simulation that looks like this. So it's much coarser. Maybe this is one of our triangular elements, and it doesn't exactly match the topography because we use slightly different data sources when we developed our mesh, and things have changed over time. Also, we have to do some sort of averaging when we apply ground elevations into our model, and so it's not fair to expect a one-to-one match here. But we want to do some post-processing to try to account for that. So this blue polygon, this might be where ADCIRC thinks the water levels are around 2 feet, and then up in the estuary, maybe the winds are blowing water up in the estuary, and we're getting 3 feet of water, and then ultimately 4 feet of water at the top of the estuary. What we want to do is expand outward this ADCIRC computed water surface so that it meets up with the correct contours in the topography. And so that would look something like this, where the our 2-foot predictions have been extended outward to the 2-foot contour in the ground surface. The 3-foot contour has been extended out to the 3-foot, and the 4-foot, same with the 4-foot. So we're adding regions along the edge of our flooding predictions that should be wet. They're just not able to be resolved in our model. And if there are houses in these regions, if there are roadways, then we will now show that they are impacted by the storm, and then NC Emergency Management can use that in their decision making. So a couple more details here. The interpolation step is pretty costly. We're taking our 600,000 points in our ADCIRC model and interpolating them onto this really dense 50-foot raster DEM. Just Carteret County alone, there's 28 million cells, and for the entire NC coast, it's 434 million cells. So really populating that raster with water levels can take up to 5 minutes just doing that interpolation. And we think there are ways to speed that up, but we haven't figured them out quite yet. So that's 5 minutes right there. It's just doing the interpolation. Then we load it into GRASS, and we extrapolate outward using this GRASS module, r.grow. And the idea here is it does exactly what we want it to do. It takes the edge of your raster and it incrementally grows it outward until it meets some condition that you specify. We made some changes to r.grow specific for our problem, so we wanted to check to see if the water level is higher than the ground surface and only grow if that test is satisfied. And so we have a special r.grow module that does that. and now we can grow by a sufficiently large radius, and then after that we check to see if there are any isolated cells that need to be removed due to hydraulic disconnectivity. At the end of that, we can convert back to polygons, bin the water surface into half-foot intervals for those polygons, convert them into a shapefile, and then send an email to our end users. So another example, but here this is more realistic. So here we're working with Carteret County, and we chose this as an initial test because it has almost everything. There are barrier islands in Carteret County, there are estuaries, there's some very low-lying topography, some coastal communities for sure. And so this, if we can get the system working on Carteret, then we feel pretty confident we can get it working for the entire coast. And so I'm going to zoom in here on a part of the barrier islands in the Cape Lookout National Seashore. And so this is an example here of the 50-foot DEM. The white space at the top is the open sound, Pamlico Sound. So there's no data there because those areas are below water. And at the lower right, this white area is the Atlantic Ocean. So again, no data there. But the stuff shown in the grayscale has elevations from 3 feet below sea level up to 25 feet above sea level in some of the tops of these coastal dunes and this barrier island. So that's each pixel here, each cell is about 50 feet on a side. And on top of that, we can overlay our ADCIRC model results. And so now I'm showing, just for reference, each of these little black X's. This is one of the points in our ADCIRC mesh. So you can really see the difference in resolution between what we're able to use in our ADCIRC model and this 50-foot DEM that was provided to us from NC Emergency Management. And so you can start to see some issues here. The AdCIRC, for this simulation, the wind was blowing out of the sound, and so the water levels are higher on the sound side of the barrier island, up to 7 feet, and then winds are probably blowing away from the barrier islands on the ocean side, and so we've got slightly lower water levels here, up to 4 feet or so. We've got some overtopping of the south part of this barrier island already. We're able to resolve that in our AdCIRC model. But here in the higher part of the barrier island, we're not able to do that. The water levels just aren't high enough. But we also haven't brought the water levels far enough into the island, including along the open coasts. There's some regions here where this is open water in the DEM, but we're not showing open water in our AdCIRC model. We have an edge of our forecast water levels that doesn't even meet the coastline. And on the backside, some of the same thing. The 7-foot water level should extend much farther onto the barrier island than they're shown here. So after we run our downscaling and our extrapolation and get our enhanced guidance, it looks something like this, where now the 7-foot water has been brought up to the backside of this barrier island and the coastal dune, and even the 4-foot water on the ocean side has been brought onto the beach. And so now there's a very narrow sliver of the island that is still above the water level for this simulation, the maximum water level. You can start to see some of what I was talking about. The water is kind of curving around some of these features and coming through, and so we're trying to maintain a hydraulic connectivity, so it is physical that water could potentially do that. And we have some regions where the 7-foot water extends all the way to the 4-foot water, and even that is physical if you use your imagination a little bit. That represents overwash and water flowing over that coastal dune and coming down into the ocean side. So even that has a physical meaning back behind it. A couple more examples. This is a before and after shot of the Newport River in Carteret County. Beforehand, AdCIRC's able to resolve these estuaries and all the way up this river. But again, we're not bringing our water levels all the way to the coastline just because we're using a different data source and we're using lower resolution, and we're not able to extend as far up in these estuaries as the water probably should go. And so on the right-hand side, this is the after image, and you can see the water really extending up into these estuaries, connecting up through and coming all the way in here. And again, these are if the water is 7 feet in this region, then it should extend into these estuaries because they are shallower than 7 feet, but we're just not able to resolve that if we're trying to simulate on the entire NC coast. Another example, this is Cedar Island in Carteret County, and again, coarse ADCIRC resolution on the relatively coarse AdCIRC resolution on the left, and then the downscaled and extrapolated on the right. And again, you can see water curving around some of these features, extending up the estuaries. And I don't know if the resolution is good enough on your monitor, but you can even see some of these agricultural channels being resolved now, water flowing up in the channels, but leaving some of the higher topography dry in between them. And so this is not an artifact of our extrapolation technique. These are actually present there in the DEM, these rows. So getting down to much finer resolution than we were able to do previously. So how does this work, or is it working well? One initial validation that we've done is just do an intersection. So take our enhanced guidance and compute how many buildings it covers. So from NCEM, they shared their data set with every building along the coastline. It has the building footprint, the first floor elevation, a lot of other information that's pretty proprietary, I think. But they use it for their planning during and after storm events. They want to see how many structures might be flooded and where the impacts would be the worst. Before the enhancement, these numbers are just for Carteret County. Before the enhancement, this AdCIRC hindcast of Hurricane Matthew was showing 2,400 buildings being impacted. After the enhancement, we've increased that by 60%. So by bringing that water level a little closer into the coast, extending it up into these estuaries and into some of the floodplains, we're showing more impact of the storm, and ultimately this will be more useful. And we've started looking a little bit at flood insurance claims to see, well, did these buildings actually get flooded during the storm? But that's very much a work in progress, and I did not get clearance to show any of that comparison today. We also want the method to be really fast. So I told you the AdCIRC interpolation takes 5 minutes, but the entire process was taking 30 or 40 minutes at first. And that was because we were operating on the entire 400 million cell raster all at once. So we parallelized them, we tweaked the scripts to allow for parallel processing on up to 16 CPUs here at NC State. We took that 400 million cell DEM and divided into 16 strips that overlap, and then we can run now on our cluster, and it takes 12 to 15 minutes for the entire process. I'd love for it to be faster, but that's workable. We can do that in real time and then send off the results to our end users. And this is an example on the entire coast. So it does work for the entire NC coast. This is in gray, the entire 400 million cell DEM, and then on top of this is a simulation from AdCIRC. And again, a zoom image here of the Albemarle Sound, and where AdCIRC is representing these estuaries and these rivers coming off of the Sound. But after we do our enhancements, we're getting a lot more water. You can start to see the fractals of the water pushing up in these small-scale channels and floodplains. So what's happening right now? We are now providing this guidance to NCEM. This script has not been worked into the ASGS, so it's not being run at RENC yet. Right now, we're running it here at NC State, and what we're doing is we're checking the RENC archive to see when the latest AdCIRC model results have been posted. We can download them and then do the enhancement and mail off our results. So we did this for Hurricane Harvey just as a test run. We were doing the enhancement for the North Carolina coast, even though Harvey did not impact the North Carolina coast. But now we have some confidence that the automated script is working and the enhancement is doing what it's supposed to. And so we are producing results now for Irma and sending them off to our end users. And hopefully in the future we can bring this script into the ArcGIS and it will all coexist with the rest of the ADCIRC forecasting. So future work, so Nelson hasn't graduated yet. In his second year of his master's, now that we've developed this tool, we're going to really try to do some science questions. And the big one in my mind is testing this hypothesis, which is if we took our ADCIRC model and increased the resolution in our unstructured mesh to match the 50-foot raster DEM, would ADCIRC then give the same water surface that this post-processing script gives? Would it bring the water into these channels and into these floodplains if it had that same resolution? So Nelson is hard at work creating a refined mesh for North Carolina, where in some regions we have 50-foot spacing to match the raster DEM. And actually we're putting our ADCIRC vertices, the vertices of our triangles, in the exact same places where the cells of the DEM are located, so that we can try to represent as closely as possible that ground surface. And if that's true, if the hypothesis is correct, then that means that this enhanced guidance is mostly physically accurate, that the water would extend into those regions and there would be this additional flooding in these small-scale regions. And if that's the case, if we can get away with this as a post-processing step, then that might allow us to coarsen our unstructured mesh that we use in ADCIRC. So maybe instead of 600,000 vertices in ADCIRC, maybe we can get away with a few 100,000 less and run ADCIRC in a faster time, and then do this post-processing to bring the water levels into these small-scale coastal features. There's probably going to have to be a balance there. ADCIRC is actually solving the equations that govern coastal circulation and flooding, and so there's reasons to expect it to be more accurate than just this post-processing step. But in a forecasting system, any gains in efficiency are appreciated. So this ties into some of my other projects that are supported by the DHS Coastal Resilience Center, and also a new project that just got funded by NSF. And all of these are looking at ways to speed up and provide this forecast guidance in a shorter time. So that's my talk. In summary, if you remember only one thing, please go to ADCIRC.org, follow the links through, and look at the forecast in real time. We're doing it right now for Hurricane Irma. The sites might be slow because a lot of people are on there looking at our results, but just have patience with us. And we're doing each advisory and some perturbations, so changing the track or changing the forward speed, which really is helpful in a case like Irma right now, where there is some uncertainty about the track. And then as part of the NCDS Data Fellowship, we've been working with NCEM to add to their workflow and enhance the guidance that we are sending to them by downscaling our model results and extrapolating them into small-scale coastal features. And we are already sending that enhanced guidance back to our end users as shapefiles. So thank you very much for spending your lunch with me, and I appreciate any questions that you have.
Thank you, Casey. We have a question here, and others, if you want to type in your questions, there is still some time to do so. I'm going to read this question back. Have you been able to do any validation of the downscaled flood extrapolation with data on the actual water heights during an event, assuming those observational data are available, of course?
Yeah, so that's the part that we're just starting. There's two ways to do that, I think. One would be to compare to ADCIRC. If we trust ADCIRC, then if we run it at the same resolution, if we increase the resolution down to 50 feet in ADCIRC, then we should get a very similar surface as what we're getting with the extrapolated post-process surface. The other way to do that is to compare with observational data, and that's where I think that building data set from NCEM is going to be really useful. It's just a matter of working with the actual flood claims to see which buildings are actually flooded And then I think we'll see that by extending the flooding out with this process, we're capturing more of the buildings that were actually flooded during Matthew or during other events.
Okay, any other questions at this time? If not, Casey, I want to thank you for spending your lunch with us because I know you are really busy with everything that's going on. And I also want to point out that Casey, part of this research is it's supported in part by the NCDS through our Data Fellows program. So thanks everyone for spending your time with us. And for those of you in the audience, remember that DataBytes is a monthly lunchtime webinar series. Mark your calendar for our next session. That will be on Wednesday, October 4th. Thanks everybody. Have a great rest of the day.